Hello, welcome to Astronomy Chapter 6. This chapter is going to be looking at the Earth and the Moon, and in doing so, thinking of the Earth and Moon not necessarily as we see them here from our own perspective, but trying to look at these two objects as a way to start doing a comparison, to compare them to the other objects in our solar system. So we're going to look kind of at some of the physical structures of these and look at sort of how they're built and how they're put together. And what you're going to see in the first half of this chapter about looking at the Earth is information that would be like the introduction to a geology course, for example. And we'll add a little bit more to that in terms of some of its astronomical properties, but mostly this is going to be sort of some of the physical structure of the Earth and then as the Moon as well. And of course, we've already talked about the Moon and its relationship to its position around the Earth and in the celestial sphere, creating phases and eclipses and the like. But this will be more of a perspective of the object itself. What is it like? What is it made of? Those sorts of things. So let's take a look at Chapter 6, which we said was called The Earth and the Moon. And the first part of this, sort of the thing that I really want to give to you to look at, on 161, you're going to see a page like this, or a graphic like this, for all of the planets that we're going to be looking at in the next couple chapters, that give you the vital statistics, sort of the snapshot of the information about these all the objects we're going to be looking at orbiting the sun. And the information that you see here, by no means am I going to expect you to memorize this information or to be able to rattle off the top of your head the density of the Earth at 5,520 kilograms per cubic meter. That's not the point of this page. The point of this page is to give you a quick reference to some of that important data. And some of the things you can see on there, like how far is it from the sun, at its closest and farthest. Remember, we said that the distance from the Earth to the sun actually changes. It's not a constant number. It's around 150 million kilometers or 93 million miles, but it actually changes slightly because our Earth is slightly eccentric by about almost 2% off of being a circle. So the Earth actually has one of the most circular orbits, very, very close to a circle, but it does change a little bit. It talks about how fast we're traveling, our mass, our size, our density, etc., etc., is given here. Very nice table of data, great reference point, and so this is a good page to make sure that you have and know where it is. The next thing that it kind of goes into is it talks a little bit about the atmosphere of the Earth. It talks about the importance of the atmosphere and these different layers and how the atmosphere changes as you go up. This is material that you would see. You would go into great detail if you're taking a course on meteorology. In astronomy, we need to know a little bit about these layers. But the real thing that matters for us is that our planet has an atmosphere. And a very good one. Our atmosphere is actually really one of the most important parts of what sets us apart from all the other terrestrial worlds. And when I use the word terrestrial, I'm referring to Mercury, Venus, Earth, and Mars. You could also throw the moon in there sometimes. Some people consider the moon a terrestrial world. But as far as the interterrestrial planets are concerned, we're the one that has the right atmosphere for human life. We have an atmosphere that is just the right size to trap just enough heat to keep us the right temperature. This greenhouse effect that we hear a lot about is describing how this atmosphere traps the heat, much like the heat is trapped in a car. But our atmosphere does many useful things, not only keeping breathable air here. It heats our planet. It moves the energy around through meteorological processes, distributes the water around, etc., etc. It also, this text goes into a little bit of a description about some of the late concerns we hear about carbon dioxide and the trend of the relationship between carbon dioxide and temperature, and what is the potential concern for extra CO2 in the atmosphere. Moving on, the physical... The geosphere of the Earth is another topic that we're going to really just glance at here. And of course, plate tectonics is a essential part for understanding how our Earth is put together. Our Earth has these plates that move all around it, like broken eggshells that are shifting around the surface, and they're being driven by the mantle underneath that is a convective material moving them along. And the interaction of these plates is where we see many unique geological processes happening. Earthquakes, volcanoes, and the like. But it is a well-understood theory that these plate and those plate boundaries are a major part of what describe the functions of our planet. This also appears to be a relatively unique thing among terrestrial worlds, that we don't see active plate tectonics going on other places. Another thing that makes the Earth unique. Then kind of going deeper down into the Earth, they talk a little bit about the idea of the layers inside the Earth, about the core and the mantle and the outer core, and of course the thing that is the immediate concern for astronomers is the effect this creates, is that the inside of the Earth is very hot, and it is metal, and it is spinning, and in doing so creates a magnetic field. Now, we're going to hear a lot about magnetic fields. You're going to hear about magnetic fields that are not only for our planet, but also for other planets. And there's even magnetic fields that are related to stars, which is a unique relationship for the material inside of any one of these large bodies to create an electromagnetic phenomenon because of what they're made of. Our planet has iron inside of it, lots of iron. Nickel does this to a lesser extent, but largely it's the iron spinning quickly, creating our magnetic field. Magnetic field ends up being important, again, for human life because it shields us from some of the more harmful radiation in space. So that's another part of what makes the Earth is our unique magnetic field. And they kind of go into show you some pretty good graphics explaining this, that our magnetic field is not all that much unlike a bar magnet, where you could sprinkle iron filings around and see those lines being created. We are, in effect, living on a large magnet. All right, moving on. The moon, talking a little bit about the moon. They give you, again, notice the vital statistics page. They give you, how far away it is, its orbit, change in its orbit. It tells you information about how dense it is, and a variety of other informations are given here. The atmosphere is almost non-existent. It is, in effect, considered an airless world. There is essentially no atmosphere around the moon. But the moon's surface is an area of real interest, and they give you some beautiful descriptions right here, showing you what's the craters of the moon, which is a fascinating subject to look at. And they talk a little bit about how these craters are believed to be formed. Of course, a crater happens largely because of an impact from another small object here. A meteoroid is used in this description, showing you how it creates not only a hole, a circular hole, but it also creates this little rebound area right here in the middle, where there is a central peak where the material is rebounded into this area right in the center, because it was, in effect, heated to the point of melting, which is a very neat concept. And then there's secondary craters that can be made if it was a big enough impact, and so on. An interesting, a whole area of science can be done here simply by looking at the craters. Now, a neat anecdotal side note here is we don't see many craters like this on the Earth. And we don't see those craters for a variety of reasons. The Earth has a lot of natural ways to either hide or to eliminate craters altogether. The first of which is that atmosphere we looked at earlier. The atmosphere itself causes most of the material coming in to burn, because as a rock or any other piece of space debris that perhaps humans even put in space, as it comes through our atmosphere, the air is compressed and it is heated, and there's frictional heating as well that heats that to the point where the object is often turned from a solid and vaporized. And so it never even strikes the ground. Now, larger impacts happen, but statistically, if you look at our planet, 3/4 of it is covered, or so 3/4 or so is covered in the oceans and water. So 3/4 of the time when an object actually makes it through our atmosphere, it hits the water and doesn't make a crater that we can see. And then any craters that actually do manage to hit land, very quickly that area is covered over by vegetation. So we see very, very few places where we see craters like this on the Earth because we have so many things that are not allowing them to show up in the first place and then sort of erase them, if you will, after they do actually happen. There are a few places. The Barringer crater in the southwest United States is a great example of that. But the moon is covered in them. And then, of course, the lunar surface is something we've become very familiar with. Humans have been looking at the lunar surface for as long as we've been around. And, of course, we have even gone so far as to send people to the moon to go try to study it. And we've figured out a variety of things by doing this. And the Apollo missions were wildly successful, although we have not been back to the moon in several decades. We did learn a tremendous amount through those missions. But one of the other things that's sort of unique about the moon is if you were to look at the back of the moon looks very different from the front of the moon. The front of the moon has these large, dark areas, right, where we see very few craters. Those are what we call mare. The mare have effectively no craters on them. But on the back side of the moon, and this is a color-enhanced image, the back of the moon is not colored like this. That would be pretty sweet if it was, but it's not. But the back of the moon is completely covered. It has almost effectively no dark mare left on it. And one of the questions as to why is it that way, well, the answer is because the moon is what we call tidally locked. And what that means is the moon constantly has the same phase to the Earth, like this. If my hand was the moon and I was the Earth, it's doing this where the same side, we always see the same side. So what happens is the Earth ends up being a bit of a shield. So the Earth is sort of blocking this side that's between us and the moon. And so we see part of it is being protected from those craters, from those impacts. Obviously, the backside is not afforded that luxury. So it has many more craters on the back than on the face that we are typically known to see. Now, of the surface, one of the things that the Apollo mission wanted to do was to try to answer the question, what is the moon made of? And I'll give you a hint. It's not Swiss cheese. The moon is, in fact, a rock, and what we have found is that the moon is made up of basically the same thing as the Earth, and specifically the same thing as the crust of the Earth. And a lot of it appears to be made out of rocks called basalt. Here's an anthracite and breccias. All of these are volcanic rocks, which lead us to believe that the moon was once in a molten state and cooled. So that is a part of the information about where we think the moon came from, is perhaps that it was once material that was made out of the Earth. And so on page 180, they talk about this idea of where did the moon come from. And the leading idea on this is the idea of an impact. Now, there is a trend in astronomy, and it's something that I often make a little bit of fun of. But when we look at something and if we don't know what happened, we come up with the answer, well, something big must have hit it. Right? So when in doubt, the answer that we always, it's a lot of times it comes to, something large, there must have been a big collision to cause this major change. Well, I say that a bit tongue-in-cheek, but the reality is collisions in astronomy are very, very important. And collisions do happen often. Large, major impactful collisions do happen, although they don't happen now nearly as often as they used to, apparently. It appears that the solar system was once had much more material, and as gravity and time have been allowed to interact, those devices or those objects have ran into each other and caused them to coalesce, if you will. But the moon appears to have once been formed from the same material as the Earth, because it is made out of the same stuff. And the last little thing they explain at the end of this chapter is they talk a little bit about the tides. And this is a great example talking about sort of a nice tie-in with some of the things we've been looking at with the idea of gravity and Isaac Newton from several chapters back. In fact, it was the idea of the moving tides that allowed Newton to take the idea of gravity and move it from here just on the Earth out into space. He said, and he realized that the moon was causing the tides. And in doing so, he realized that this idea, this concept, of gravity is not just for here on the surface of the Earth. He realized that gravity must be for everywhere. Gravity is for everything. And so that is where the concept of universal and mutual gravitation come from, is largely from the concept of the tides. That the moon pulls on the Earth and causes that water to slosh to one side or the other, creating the effect of the tides. There's also a little piece right at the end of the chapter talking about the fact that the moon is moving away from us, and we use laser beams to do this. It's a very cool concept. We shoot lasers at the moon and measure the distance from the Earth to the moon very, very precisely. And we do this because of the Apollo astronauts left little reflectors on the moon. That we shoot those little reflectors and they bounce back at us, and we can measure very, very close, very, very precisely the distance from the Earth to the moon. It's a neat concept. Okay, so that will get you going on Chapter 6. Make sure, again, you're reading the text and that you're taking a look at the PowerPoint associated with this chapter. You should be good to get going on the homework.